This lesson starts up our unit on nomenclature, and so in this lesson we're going to talk about 5 things. We're going to talk about cations and anions. We'll talk about balancing ionic charges. We'll talk about polyatomic ions, oxygen stabilized polyatomic ions, and the old system versus the stock system of naming certain ions. In general, this unit is going to be on, I said, nomenclature. The basic root of this word here is first the word nomen right there, which means name, clature, which means sort of a process of organizing things, and so organizing it by its name. So basically what we're talking about here is naming compounds. And so on to that. First topic here is cations and anions. And so to understand these is that cations and anions both have at their root the word ion. And so for both of these are both types of ions, but they're different types of ions. Cations are positive ions, anions are negative ions. And so you can sort of, one way of looking at this might be to say, you've got the little T is like a plus sign right there. That's one way of remembering that cations are positive. Or you could know that the root an or a like that usually means not. And so anion would be like a negative ion, like a bad ion. Not necessarily bad, but you get the idea. So as we talked about in the last lesson in the previous unit, is that elements that tend to be on the left side of the periodic table tend to be positive charges, so those tend to be cations. Ones that tend to be towards the right side of the periodic table tend to form negative ions because they attract electrons because of their small size and such. So they're close to the nucleus, so they tend to be negative ions. Now, whenever we have cations and anions, in order to name them basically is if we have one element, just one element that's become an ion, that it's considered to be a single or monatomic. So the root here is like like a monocle, means there's like a glasses thing that has only one lens. So mono is one, and so naming single ions, we're talking about single ions. The rules are different depending on whether it's a cation or an anion. If in a compound you have a cation, then the name of the ion basically is just the name of the element. So if I had something like sodium, Na, if go ahead and take out your periodic table and take a look at sodium, you'll see that sodium on your list there says it has a charge of +1, and so that +1 tells you, number one, it's a cation, and number two, it tells you its charge is +1. So we've got that information there. Now for cations, the name in any compound is just the name of the element, so it would just be sodium in that case. If we looked at, say, strontium, strontium's a little bit lower, a little bit farther to the right, and you see it as +2. Also a cation, so if we were basically naming something, we'd say it's just strontium. Now, on the other hand, if we were to go to something like, say, chlorine, now chlorine's over on the right side, that means it's likely to be an anion, and sure enough, if you look at chlorine, it says +1, +5, +7, -1. The charge that's most common is going to be the -1, because it wants to gain one electron to get, it can gain one electron to get to a full set of valence electrons from 8. If it gained more than that, it wouldn't want to do that because they'd have to go up to the next energy level. So for chlorine being an anion, then the rule is basically this. So we have chlorine. To name a chlorine ion, basically what you do is you drop the last syllable, so "ine" drops out, and you're going to add to the end of it "ide." So the chlorine ion would be chloride in that case. That's what you do for anions. If we had something like, say, oxygen, we look at oxygen. Oxygen has a charge of -2, means it's an anion, and so in this case right here, instead of oxygen, we drop the GEN and add IDE for oxide. And so the ion of oxygen would be oxide in that case. And so that's how you go about naming cations and anions. Cations just take the name of the element. Anions drop the ending and add IDE. Alright. So, balancing ionic charges. Anytime that you have two ions, they combine to form a compound. Basically what they're doing here is that you have the one that is going to be a positive ion is going to give up its electron to the one that's going to be a negative ion. Effectively, if this is a covalent bonded element, or covalent bonded molecule, that would mean basically they share. The word here is co, and so they would share that electron. In other cases, you have what's called an ionic compound. In that case, basically the one that is more electronegative, that means wants to take the electron more, is going to steal the electron from the other ion and run off with it. And that's going to be the case of things that are usually salts tend to do that. But in general, is that if one element comes and takes another electron away from another element, the total number of electrons never changed. And so if it took one, that means it has a charge of -1, but the other one has to have a charge of +1. Those sets of charges have to balance out. And so what you'll find is in any element, or any compound, any molecule, is the total positives and total negative charges have to add up basically to be 0. And so the absolute value of both has to be the same. So if your negative charges add up to -6, your positive charges have to add up to +6. If your negative charges add up to -10, your positive charges have to add up to +10. And so overall, you're going to end up with a neutral molecule. And so, as it says, the ionic charges have to be balanced. So let's try this out with a few of them. We have sodium chloride, and so the first bit of doing this is going to be saying, okay, we have sodium. So looking for sodium on here that's Na. We have that right there. Chloride, the key part in looking at this is recognizing it has that IDE, and so we're looking for the element that starts chlor, and that's going to be chlorine. And so we look for chlorine, and chlorine is over there on the right side. And so chlorine, I'll make it a different color just so we can remember what we got here. Now to work this out, we've got to make sure that the ionic charges are balanced. So we look at sodium. Sodium has a charge of +1. And so we got +1 for sodium. Chlorine, on the other hand, says it is +1, +5, +7, -1. Now, if it were +1, +5, or +7, there's no way these could balance. You can't add up two positive numbers and end up with 0. You wouldn't have a neutral one. The chlorine has to be, in this case, the -1, and that sort of makes sense because, it's ends in "ide." It has to be an anion. And so, by definition, it has to be the -1, and turns out chlorine's most common valence is going to be -1. So, in this case, NaCl, +1 plus -1, that equals 0. These are balanced. So our overall, we're already where we want to be. We've got the formula here. So we've got our total one, just NaCl. And that's it. All right. So our next one, aluminum sulfide. So our cation here is going to be just aluminum. That one's pretty straightforward. Now the next one is sulfide. It does end in IDE, so that tells you that's an anion, as well as the fact that since aluminum is positive, it's going to have to be an anion. So we look up sulfur. Sulfur is +4, +6, -2. And so in this case it has to be -2. Whereas aluminum, if you look it up, is only one thing. It's only +3. And so we only have +3 for that. And so the question is, how do we get these to balance out? Because unlike the sodium chloride we saw before, 3 and 2 do not add up to be 0. And so to do this, what you want to do is you want to look for the least common multiple. And so what number it will both evenly divide 3 and 2. And so least common multiple between 3 and 2 is just going to be 6. And so how many aluminums do I need to have a total of +6 if each one is +3? I need 2 of them. Because 2 aluminums times the +3 gives me a total of +6. For the sulfurs, each one is -2. That means to get a total of -6, I have to have 3 of those. And so my overall formula for aluminum sulfide is Al2S3, like that. And so that's how you'd work that out. All right. On to our next one, calcium bromide. First thing we look up is calcium. It is on the front because it says that normally is the rule, or always the rule is that cations are going to come front and then anions are on the back side of any written out formula. So we have calcium bromide. The first one here is calcium, Ca. If we look at the charge on calcium, it says it's +2. So +2 is the charge on calcium. The next one is bromide. Ends in IDE, and so since it ends in IDE, that tells us it's the anion. And so bromide would be bromine. So we put bromine down here. Bromine is +1, +5, -1, but it has to be the negative. So -1. These numbers do not match up to start with, but we say what's the least common multiple between 1 and 2? What do they both go into evenly? Well, we'd have 1 calcium, and we would have to have 2 bromines. And so I have to have 2 bromines right like that. So our final one is going to be CaBr2, like that, because 2 bromines, 2 times -1 is -2, plus 2 is 0. So that works out for that one. Our last example here is carbon nitride. So for carbon nitride, the first one is carbon, and so we'll write out the cation as carbon. Carbon, if we look at it, is +2, +4, -4. So there are 2 possibilities. It could be +2 or it could be +4. Now, whenever you've got a case like this, is that for writing these out, is that technically is that this carbon, there should have been something to indicate what valence that carbon has. Probably it would be in between this. We'll talk about that in just a second. Since it's not here, what we're actually going to find is that the most common valence state for carbon would be 4, would be +4, because if you look at it, it's got 4 valence electrons. And so that means it could lose 4. If it only lost 2, that wouldn't be as common, because it would have to, it would still have a couple in its valence shell, but it wouldn't have gotten rid of all of them. So this is going to be carbon 4, and so that's +4. Now the other piece here is nitride, and so nitride, drop the IDE, nitrogen would be that. And of course, nitrogen is our other one that is most uncommon here. If you look at it, it's ±1, ±2, ±3, +4, +5. So this could be -1, -2, or -3 for its charge. Taking a look at nitrogen, though, you can see that it would have to gain how many electrons to get a full set of valence electrons, to get to 8. So it would have to gain 3 more. So nitrogen is one you just sort of have to remember. When it's negative, is almost always going to be -3. And so you just sort of have to remember that and memorize it. So unless you're told otherwise, nitrogen is going to have a charge of -3 when it's an anion. So we've got these two right here. We got 4 and 3. Least common multiple here is 12, and so 3 times 4 gives you that one right there. 4 times 3 gives you 12 right there. So those two would cancel, and so our final compound is C3N4 for carbon nitride. All right. Now, next topic here is polyatomic ions, and the root here is the word poly, meaning many, atomic, meaning atom, so it means literally many atom ions, like that. So that's basically what a polyatomic ion is it is not just one particular atom, like chlorine becoming chloride. It would be several atoms that are stuck together, that travel around together, but have a charge when they do so. And so you have a sheet that is a list of common polyatomic ions, and so get that out if you don't mind. As well as you probably also want to get out your nomenclature guide, and so that one right there is going to tell you a little bit about some of the stuff we've already talked about, but we'll also talk about some of these polyatomic ions. The list of sheets that you have for your polyatomic ion sheet gives you a list of different polyatomic ions, what their charges are, what their formulas are, and what their names are. Now, in terms of the way the names work, we're going to talk a little bit about that, is that there are 2 types of polyatomic ions we're going to run into. One type is going to be basically the oxygen stabilized polyatomic ions. We'll talk about that in just a second. The other type are sort of the odd type, the type that there's no real rhyme or reason that we're going to cover as far as why they're named what they are. Those would be things like hydroxide or cyanide that look like, based on their ending, that they'd be a monatomic ion because it has "ide" on the end, but they're actually not. You just have to remember that that's what they are. Or actually, well, it's on the sheet. You have to use the sheet to figure out what they are. So that's what you've got for your basic naming conventions there. These are covered on the back of your nomenclature guide. If you take a look at number 15 on the back there in part 2, it says if the anion portion of the compound is polyatomic, go to 19. And then it says, then it takes you to 19. It talks more about these oxygen stabilized. It says most polyatomic ions are composed of an element combined with some oxygen atoms. So let's take a look at that case. See, we've got the general form of oxygen stabilized polyatomic ions is that they will have an ending that is 8. Like, for example, carbonate or nitrate or things along those lines. And so those would be examples of a standard general form oxygen stabilized polyatomic ion. And so if we were to sort of use this example, we would say, let's see, nitrate. So nitrate would be one that we have right there. That would be the general form. Now, this is what it talks about, says on number 19. So it says the name of the ion is the stem of the non-oxygen element with an ending that describes the number of oxygen atoms present. Nitrate, as you look on your polyatomic ion sheet, is just something that has, well, I mean, it's NO3, right? And so based on this, what does this say? We have a nitrogen right here, which is why it has the niter on the front. It has 8, which indicates it is oxygen stabilized. So nitrate, the root there means that it's nitrogen, and the 8 means it's got some oxygens attached to it. So that's 19. So, and then it actually tells you to go to 21, which talks about this, that the most common, most stable is added by adding 8 to the stem of the non-oxygen molecule, like sulfate for SO4. And so sulf tells you it's sulfur, the 8 tells you it's oxygen stabilized polyatomic ion. So we got nitrate here. Now, if it has one more oxygen in the general form, that is going to be what's going to happen if you have 22. Say that it says NO3 is what it has on your polyatomic ion sheet, but you're given something that says it's NO4. That's not nitrate, but it's related. And so if it has one more oxygen in the general form, this is what happens on 22. It says it's given a prefix of per, short for hyper, before the name. And so in this case right here is that what you'd have if you had one more oxygen, it wouldn't be nitrate, it would be pernitrate. You take the old one, nitrate, you add per to the front, and that tells you it's going to have one more oxygen. So pernitrate would in this case be just NO4. Now technically these should have charges on them. We won't worry about it right now, but that's basically what we've got there. So pernitrate would be NO4. Now on the other hand, if it had one fewer oxygen, that would be going to number 23 on your nomenclature guide. If it says one less oxygen in the 8 form, the ending is changed from 8 to ite. And so instead of nitrate, this becomes nitrite. And nitrite would just be, instead of NO3, it would just be NO2. It's lost one from the 8 form. And so one fewer oxygen in general form is nitrite. Now, similarly, if it loses 2 oxygens from the general form, that's number 24 on your nomenclature guide. It says if it contains 2 less oxygens than the 8 form, or 1 less than the ite form we just talked about, it gains a prefix of hypo in front of the previous one. So this would be hyponitrite. The ite indicates that it's losing stuff. The hypo indicates it's losing more than just one. And so this would just have a charge of NO, or just have a formula of just NO. And so that's going to be what you have when you have 2 fewer. So the general form that's on your polyatomic ion sheet always end in 8. If it has one more oxygen, it becomes pernitrate. If it has one fewer oxygen, it just becomes nitrite. If it has 2 fewer oxygens, it becomes hyponitrite. The same rules apply with all the other oxygen-stabilized polyatomic ions. Carbonate is the general form. One more oxygen in carbonate would be percarbonate. One fewer oxygen would be carbonite. Han Solo accepted. 2 fewer oxygens would be hypocarbonite. And so that's how that would work. All right. Some elements, like the carbon we talked about before, are considered to be multivalent elements. And when we say multivalent, what that means is they've got more than one possible valence state. If you take a look at iron, iron says that it could be charged of +2 or +3. And the question is, how do you know which one to use? And if you take a look at your nomenclature guide, this is what we're talking about on number 6 on the front, on part 1. It says the metal is a transition element or one which is multivalent. Information must be included to tell which oxidation state is present in the compound, because otherwise you don't know what it is. If I just say I've got iron oxide, is that you say, well, that could be iron +2 oxide, or it could be iron +3 oxide. Those are two completely different compounds. One is sort of reddish, the other tends to be greenish, and they have different properties too. So there are 2 ways of doing this. there is the stock system. And stock system is what is described on number 8. It says just a Roman numeral indicating the metal's valence is placed in parentheses directly after the metal name. And so if we had, in this case, let's say we do have iron, and we have iron, and it's going to be iron minus 2, or sorry, plus 2. Can't have iron minus 2. It's not possible. So iron minus, or iron plus 2, here, using the stock system, that this would basically just be, you'd write it out as iron and then parentheses 2. And that looked absolutely horrible, but you get the idea. Iron 2 is how you do this in the stock system. Now, old system, and okay, well, first thing before I go on, stock system, you're going to find you only use this with cations, and so you don't have to worry about ever having like a negative 2 in parentheses. It's always going to work out just that way. It's always going to be a positive one for what you've got on your stock system here. So that's the stock system. That's how it works. I personally find the stock system is the easier of these two systems to use, and the fact is it is the more modern system. I mean, technically you probably ought to use the stock system if you have a choice, but there are a lot of people that still do use the old system. The old system is described on number 7. It says in the old system the ending of the metal name is changed either to us, O-U-S, indicating a smaller oxidation state, or to ic, indicating the larger oxidation state for the metal. So in this case, if we have iron 2 right here, we have Fe plus 2, we say which one's larger, 2 or 3, because those are the two valence states. Well, 3 is larger, so in this case it says that us is a smaller oxidation state, and so normally you'd say this would be ironous, except this is where the old system gets even more complex. Fe, that's symbol for iron. Fe doesn't look anything like iron, doesn't have any F's or E's in it. The reason why is because it uses the Latin term, and the Latin word is ferrous. Or fer is the root here. And so basically, if we had iron 2 like this, it would be ferrous, is what you have here. On the other hand, if we had instead of iron 2, if we had iron 3, then iron 3 would just be for the stock system. Iron 3 like that. But for the old system, this would be ferric, because the fact that 3 is the larger of the two valence states, and so it gets the ic ending on the end of it there. For the most part is that these Latin beginnings on these you sort of have to just have memorized, and you'll run into them periodically as we go through here. A quick way to know whether or not you have to use a Latin symbol or Latin name on these is to look at what the symbol is. If the symbol doesn't look anything like the English word, Fe does not look anything like iron, you're going to have to use the Latin. Same thing is true for things like say, copper. Copper is Cu. There's no U in copper, and so instead it would be cuprous and cupric. And so there are things like that. Tin is Sn, no S in tin, and so tin would be stannis or stanic if you have things like that. So that's basically how you use the old system. As you can see, it's probably a lot easier to use the stock system, but you will be expected to know how to interpret from old system to a formula, even if you don't have to name it using the old system if you're given just a formula. Alright, so let's try some practice on some things. First thing is, what is the appropriate name for the following? And we can use our nomenclature guide to work through this. And so in our first one right here, we need to identify what is the cation and what is the anion. And so that the cation is always on the front, and so this Na2 is going to be part of the cation, and we know that the CO3 is going to be the anion. And so once we've got that, let's go on through what we've got here. So the first one, part 1 on your nomenclature guide, says if the cation is a metal, go to number 5. Well, we look for sodium. Sodium is way over on the left side of the periodic table, so it is a metal. We go to 5. It says the metal has only one common valence or oxidation state. The first name is the name of the metal. And so sodium is only +1. And so that means we can just go ahead and say that we know this is just going to be +1 right up here. And so once we've got that, we can just go on to the next part. Now we're going to name the anion, and we're on 14, but that street goes to 15. It says if the anion portion is polyatomic, more than one element, go to 19. CO3. CO3 is definitely polyatomic. It has both carbons and oxygens there. Now, so then we're going to go to 19. It says, is this oxygen stabilized? Yes, it is. It's got those oxygens on the end. And so we go on to 21, it says. And so the most common ones end in 8. And so let's look on our polyatomic ion sheet. Is CO3 there? Yes, it is. CO3 is there. It's carbonate. And so in this case, our first part of this we said was Na, is just sodium. So we say sodium right here. Our last part of this is carbonate because that is the one on the polyatomic ion sheet. So our name is going to be sodium carbonate. That's what this first one is. Let's take a look at the second one, LiBr. Going back through, our first thing is let's identify what cation and anion are. Cation's lithium. Anion is going to be bromine, and so we've got those two set up. Now to do this is that we say, is lithium a metal? Far left side, it's on the left side of the stair-step line, so it is a metal. We look at its valence, it says only +1, so that's all it is. And so since it's just +1 there, that's all number 5. The first name is the name of the metal. We can just go ahead and start off just by saying that what we have here is just lithium is the first part. So lithium is the first part of the name. The second part is Br, and so that flips us over to the back. So on 15 it says, is it polyatomic? Nope, it's just bromine. So we go into 16. If the anion is composed of only one element, the second name of the compound is formed by changing the ending to "ide." So we go and we have bromine, but instead of having the "ene," we drop the "ene" and add "ide." So our answer here is lithium bromide. That's what we've got for that. Our next one, MgSO3. First thing, identify cations and anions. Cations on the front, so Mg is your cation. SO3 is on the back, so that's going to be your anion. So Mg, is it a metal? Is the first question it asks on the nomenclature guide. And we look for magnesium. It's element number 12, and so the answer is yes, it is. Is it multivalent? Is our next question, and it is not. It's just +2, which means the name is just the name of the element. So if we start off here with just magnesium, like that. Okay. The next part is SO3, so we go on to the back for our anion, and it asks, is it polyatomic? Yep, we got sulfurs and oxygens. And so we go on to 19, is it oxygen stabilized? SO3, so yes it is. So go to 21. And so the most common form is the 8 form. We look on the polyatomic ion sheet. Is there an SO3? No, there's not. There's an SO4, but not an SO3. SO4 is sulfate. Well, this is a similar form, but it isn't the same as the one on the sheet, so we go into 22. Does it contain one more oxygen in the 8 form? Well, the 8 form's SO4. One more would be SO5. That's not this. 23. Does it have one less oxygen in the 8 form? SO4, drop 1, we SO3. Yes, it does. And if that's the case, we change the ending from 8 to "ite", so instead of sulfate, we have sulfite, and so this would be magnesium sulfite. Just like that. And our last one that we've got here, FeOH2. So let's break this down into our cations and anions. Cation is Fe, anion is OH2, just like that. And so in this case, when looking at this, we say that the first part is Fe. Is it a metal? Yes, it is. We go to 5. Is it multivalent? We look at Fe and that +2 +3. Yes, it is multivalent. But the question is, which one? Well, we don't know. So for right now, to start with, we just have a question mark there. We can't answer this until we figure that out. To do that, we've got to look at the back side of what we've got, at the anion. The anion is OH. So looking at that, is it polyatomic? Yes, it is. It's OH. Is it oxygen stabilized? It has an oxygen in it, but actually this is not an oxygen stabilized one because of the fact that the oxygen is on the front side, not the back side. It's not HO, it's OH. That sort of gives you a hint. And so we go on from that one to number 20. It says there are very few. They don't fit the naming rules normally. We look it up on the sheet, and we do see there is an OH there. OH is hydroxide. And so we can say just right off the bat here, we know the ending part of this is going to be hydroxide. But more importantly than that, we also know that the charge of hydroxide is -1. It says that on your polyatomic ion sheet. And since we have 2 of them, that gives a total charge of -2. To make this balance, that means that the iron has to be iron plus 2. And so since it's iron plus 2, that lets us name this. We now can say that this is going to be iron 2 hydroxide, or if you wanted to use the old system, since it's the smaller of the two, then it would be ferrous, because OUS is the smaller one according to what it talks about on the old system section, one number 7 on the front, be ferrous hydroxide. Both are correct. So that's how you go about doing naming particular compounds. Let's now look at doing the opposite. Find the formula for these particular things. So our first one here is potassium chlorate. And so we start off with potassium here. And so let's look up a couple things. One thing we're going to look up is, let's see what the symbol for potassium is. Symbol for potassium is just K. So we know we got a K involved here. The charge on potassium is +1. So let's write that up here. That's going to tell us how to balance. The next part is chlorate. One thing we should sort of recognize when we see that chlorate is the fact it's got the 8 on the end. If it were just an element by itself, that would be "-ide". 8, remember, means polyatomic ion and oxygen stabilized. So we look at our polyatomic ion sheet and we look up chlorate, and we see that chlorate is, I don't remember what chlorate is off the top of my head here. Let's see, chlorate, do I have that available? Give me just a second here. Okay, so chlorate is ClO3. So ClO3 is what we have for that. And that is going to be ClO3. And that, if you look at that on your polyatomic ion sheet, that has a charge of -1. And so in this case right here, these already balance. And so since they balance, our final formula is just going to be KClO3, since we already have a balanced valence on this. Our next one here is tin-4 oxide. Tin, the symbol for that, if you look it up on the periodic table, you can see the symbol for tin is just SN. We know we've got that there. And even easier, it tells us it's tin-4, which means this has a charge of +4. Don't even have to look it up for that one. The next part here is oxide. It ends in IDE. The IDE ending, remember, is going to generally mean it's an element by itself. And in this case, ox would be oxygen. Oxygen, if we look that up, its negative charge is -2. So to get this to balance, these don't balance just yet. We have to have least common multiple between 4 and 2 is 4. So we'd have to have 2 oxygens to get it to there. And so we put on a 2 right there. And this gives us our final result, SnO2, just like that. Our next one is magnesium hypoiodite. And so magnesium, we look that up, Mg, it has a charge of +2. And so we can say +2 for this. Mg is the symbol. Hypoiodite, if we have an ending on that of ite, that indicates that what we've got here is a polyatomic ion and one that's reduced. But it also has a prefix of hypo. And so what we're going to want to do here is, number 1, is just go ahead and look up iodate, because that's going to be the root here. And so if we look up iodate, let's see what we get. We get IO3- for that. And so for that guy right there, so we get IO3. The minus indicates it's a -1 charge right there. And so, won't pick up my little thing. There we are. So we have -1 to get these to balance. We have, made one little mistake here. IO3 is iodate, but in this case we have hypoiodite. And so since we have hypoiodite, that means that the ite part means we lose 1, IO2. The hypo means we lose another one, which is be IO. And so to get that to work, we have to get rid of that. That's not what we want. We have IO, because it's lost 2 of its from the iodate, the IO3 that's on your polyatomic ion sheet. Its charge is still -1. Remember, the valences do not change if you change from 8 to ite. But we do have to balance this, because we're going to have 2 hypoiodites to balance out that +2 on magnesium. And so we have to have 2 of those right there to get it to balance. And so this is what we have. Mg, open parentheses, IO2. And that's going to be magnesium hypoiodide. The next one that we've got here is going to be ferrous nitride. And so I think I just erased everything else. I'm sorry about that. So for ferrous nitride, basically what we'd have here is the first part is this ferrous right up here. We're going to have to try to identify exactly what that is. And so for ferrous, we say that doesn't look like any element we're really familiar with, except for the fact we've already seen it a couple times here. But ferrous does look like it would have the symbol of Fe, and so that's going to be iron right here. And so we've got iron as our first one here, but which iron is it? Iron's multivalent. It's +2 or +3. Key here is OUS. OUS means it's the smaller of the two, so this is going to be iron +2. So we've got that here. The next part is nitride. Ending is IDE, which means it's just by itself. So it's just nitrogen, but what's the valence? Nitrogen's that one that's got all sorts of valences, 1 through 5 and 1 through 3 negative, but we said that nitrogen's the one you have to memorize. It's just going to be -3 for that one right there. And so to get these two to balance, that we've got to have least common multiple here is 6, and so we have to get this to work 2 nitrogens, and we have to have 3 irons to get that to work. And so our final result here is Fe3N2. That's ferrous nitride.